Okay, guys, we're going to pick up where we left off last time. We were talking about rolling motion, and we were using energy and thinking about using energy considerations, specifically energy conservation, to analyze the motion of a rolling object. As I mentioned, now we need to talk about forces in rolling. For one reason, you can't always evaluate a system using energy. There are certain things you can't really get at with energy, and it's also the case that it's good to know what's happening in terms of forces for objects that are rolling. I'll warn you that in certain cases this can be a little bit tricky. So let's start off with a case that maybe isn't too bad, and then maybe at the end of the video we could take a look at maybe a slightly less intuitive situation. I'll give one apology there. Maintenance folks are doing work outside my window, so you may hear the blowers going, so apologies for that. Well, let's pick up with a similar type of scenario that we had last time. Let's imagine we have a ramp. Here's that ramp, and we can say that it has some angle above the horizontal here, theta. We define that angle as theta, and we've got that same disk that we had before. Here's that solid disk. We'll say that that disk has a mass m and a radius r. And maybe now, rather than wanting to know what is the speed at the bottom, I might want to know what is the linear acceleration. What is going to be the linear acceleration of this disk, a as it rolls, this is rolling, as it rolls down that ramp, and we're assuming smooth rolling motion. So the first thing that we have to do here is think about the forces that are acting on this disk. And I'm actually going to kind of zoom in on this a little bit, or a lot, for our purposes for this here. And if I think about the forces that are acting now on this disk, I want to draw the forces from their points of application. And you'll see maybe in a minute why I want to do that. So first of all, the first force we have is gravity, and gravity acts at the center of mass of the disk. So there's gravity, mg. We also have a normal force. The normal force comes from the surface of the ramp, so where the disk touches the ramp. So I'm going to draw the normal force as emanating from that point of contact. There's the normal force. And then finally we have the friction force. And here you have to ask yourself, what's the direction of the friction force? Your first instinct might be, oh, the friction force has to be up the ramp because the block's going down, or the disk is going down the ramp. But you can't assume that when you're talking about rolling motion, because sometimes your intuition can be wrong. So the way you have to think about it is this. We know that there's going to be a friction force here, and that friction force is the force that's supplying torque. Gravity provides no torque because it acts at the center of mass, so there is no R. The normal force is perpendicular, the force is parallel to the R vector, so there's no torque being supplied by the normal force. So the only force that can possibly produce torque here to cause this thing to start spinning is the force of friction. So there has to be a torque due to friction. Another way of thinking about that is if this ramp were frictionless, there'd be no way for that disk to roll. The disk, if it were a frictionless ramp, the disk would slide down the ramp and it would not roll at all. So we need to have friction in order to have this thing spin, to have that rotational component of the rolling motion. So what I might ask myself is, okay, if this disk is going to roll, what way is it going to spin? Is it going to spin in a clockwise direction, or is it going to spin in a counterclockwise direction? And I think it's fairly obvious if you think about it that it's going to have to spin in a counterclockwise direction if it's going to roll smoothly down the ramp. Which means that the torque provided by the friction right here, or the force of friction, has to be this way. Has to indeed be up the ramp. So in this case, maybe your intuition was accurate. The friction force is indeed going to be up the ramp. And the reason for that is we have to imagine that that friction force is supplying a counterclockwise torque. If the friction force were down the ramp, the torque would be clockwise. Since, as we noted before, this is smooth rolling motion, then the instantaneous velocity of that point at the bottom there of the disk has to be 0. So this is a static friction force. So I'm going to label that Fs to remind myself that it's a static friction force. There, we can't have any relative motion between the disk and the surface, otherwise it wouldn't be smooth rolling motion. Okay. So now, zooming back out a little bit, maybe I'll zoom in a little bit more. Now I want to think about how am I going to find the acceleration of this disk. And the first thing I might do is say, aha, I know Newton's second law, F net equals ma. So my F net equals ma equation is going to look like this, mg sine theta minus Fs equals ma. Okay, that's Newton's second law written in a linear format. So this is F net equals ma, right? Now, if I've given you m and I've given you r and I've given you theta, I couldn't calculate a here because I don't know what Fs is. Fs is not itself a given in this scenario. So I have to think about another equation I might be able to write that would also involve Fs, and that's also going to be a Newton's second law equation, but a Newton's second law equation for rotation. Since that friction force is creating the rotational motion, I want to write a torque equals I alpha equation. So my torque equals I alpha equation, as we noted, the only force producing torque is the static friction force right there. So my torque equation is going to be Fs times R equals I alpha. So that's a torque equals I alpha equation where, again, right, this thing right here, that is the torque. All right. Well, you might say to yourself, I don't know I and alpha, but maybe we can substitute in our expression for I of a disk, and we can remember that there's a relationship between alpha and the linear acceleration. So let's do that. I could rewrite this equation here. I could rewrite that, or maybe I'll write it below since I'm running out of room here. I could rewrite that as Fs times R equals 1/2 mr squared. Remember, the expression for the moment of inertia of a disk is 1/2 mr squared. Alpha is A over R. And now I notice some things which are quite nice. All of these R's are going to go away. You might not immediately notice that, but if I multiply both sides by R, I would end up with an R squared on both sides. So all of these R's are going to go away, which is quite convenient. And what am I left with? I'm left with Fs is simply equal to 1/2 ma, which I now can substitute 1/2 ma in, right? I can substitute this in right up there. And I'm going to end up with, if I continue down here, so now I'm continuing from this equation with that substitution made, I end up with mg sine theta minus 1/2 ma equals ma. Now I'm going to combine like terms. I'm going to add 1/2 ma to both sides. Or actually, you know what I might do is just immediately get rid of all these m's. There's an m in every term. I might get rid of those. And I'm going to get g sine theta equals, adding 1/2 to both sides, 3 over 2a. So a is 2/3 g sine theta. We might compare that to the situation of what would happen if there were no friction. If there were no friction, the disk would slide down the ramp, and you can convince yourself that the acceleration in that case would be g sine theta. That's the acceleration of something sliding on a frictionless ramp is simply g sine theta. So this acceleration is less. It makes sense that the acceleration, I think it makes sense that the acceleration is going to be less in this situation because we have this retarding friction force. The friction force is opposite from the force of gravity down the ramp. So maybe it makes sense that you're going to have a slightly smaller acceleration. So that's somewhat involved, but it's not totally unlike types of calculations we've done before. I mentioned at the start of the video that sometimes it's hard to think about the directions of some of these forces. So I might imagine the following situation. I'm going to take the exact same case, but now I want to imagine that with this ramp that we have that same disk. I'd like to imagine that the disk is rolling up the ramp. So now it begins with some initial velocity, and now it's rolling up the ramp. So here is that same disk here, and now it has of V initial up the ramp. But of course, it's going to have an acceleration, which is down the ramp. Right? It's going to slow down. It's going to have an acceleration down the ramp. So to evaluate this situation, again, assuming it rolls smoothly, we're going to have we have to start, as we did before, by thinking about the forces. And if we do that now, so here I have gravity acting from the center of mass, just like we noted before. I've got the normal force acting from the point at which the disk touches the surface, there. And now I have to think about the direction of the friction force. Now, if initially the initial omega of this this disk is clockwise, which it has to be if it's rolling up the ramp, omega initial is this way, but that omega has to be decreasing because it's slowing down, right? And our requirement, remember our requirement for smooth rolling motion, V has to equal omega R. If this is accelerating down the ramp while moving up the ramp, that means that V is going to decrease. And if smooth rolling motion is going to happen, then as V goes down, omega has to decrease. So that leads us to believe then if the omega is going to decrease and the omega is clockwise, then the alpha has to be counterclockwise. And if the alpha is counterclockwise, that means that the torque must also be counterclockwise. And the only way to get a counterclockwise torque is for the friction force to be going up the ramp. It is, again, a static friction force because if it's smooth rolling motion, this point here has an instantaneous velocity of 0. I think for most students, even for me, that's pretty non-intuitive. We're not used to having friction forces going up a ramp. But in this case, the friction force is going up the ramp. And to reiterate again, why is that the friction force is the only force supplying torque. And since the alpha has to be in the counterclockwise direction, then the friction force has to also supply a torque in the counterclockwise direction, so friction is up the ramp. So now if I were to go ahead and set up my Newton's laws equations, we would get something a little different than what we got last time. Maybe I'll do this right here quickly. I'll say mg sine theta, that's the force going down the ramp, minus Fs equals ma, and I would say that Fs times r equals I alpha. And you can sort of walk through from there. It's essentially just what we had done before. The only thing that's perhaps a little bit surprising here is that the friction force is up the ramp rather than down. In the case of sliding objects, we never saw this. In the case of sliding objects, we said the friction force is always opposite the direction of motion. Here, that's different. So I just want to call that out. You'll have some practice problems where you're going to have to do a little bit of work to kind of noodle through, okay, what's the direction of all of the forces? And I just remind you to remember this relationship of thinking about the torque and the direction of the alpha determining the direction of the torque. So that's all for now. Next time, if all goes well, we'll see how things are going. Next time, I hope to talk about angular momentum, totally different topic.